I'm going to show you the second energy method called Castellano Principle. This principle is also developed based on the work and energy principle. So imagine that I have a structure under an external force of F, and the structure has deformed under equilibrium. So work and energy principle says that W, the work done by the external force, should be equal to the strain energy saved inside the structure. So the force versus deformation curve follow this linear straight line, which indicating that the force has been applied onto the structure in a quasi-static way. And the slope of the force deformation is K. So the work done by the external force F is equal to 1/2 F times delta F, which can also be written as F divided by 2 times F over K. The strain energy is summations 1F component force times component deformation. And again, the component deformations can be expressed in terms of its component force. So this is the strain energy expression. As we know that the component force, small f, can be obtained from the external force, capital F. So they are functions of external force, F. So if we use that relationships, it tells us that work done by the external force, F, is equal to the strain energy U, and both of them are functions of external force, F. Now I disturb the structure away from equilibrium by holding deformation constant but disturbing the force by introducing additional virtual force into it. So I disturb force F to F plus delta F. So here is the work and energy principles. So I can use the Taylor series expansions and retain only up to first order. I give the second equation. According to the original work and energy principle under equilibrium, so WF should be equal to UF. So I can cancel the first term on the left and on the right. So this is what I will have. It tells me that run W over run F is equal to run U over run F. So what is run W, run F? So W is the work done by the external force. It is a function of F over 2 times F over K. So if I take run W, run F, then that will give me F over K, which is deformation. So as a result, the left-hand side reduces to deformation of the structure. So here is the equations. So this equation is the Castellano equation. It says delta F is equal to run U over run F evaluated at the external F. So this equation is very useful because it depends on how the strain energy is constructed. It can be applied to truss structure, to beam structure, to frame structure. So the truss structure strain energy expression is U equal to summations F squared L over 2EA. So you can take this strain energy expression for truss and substitute into this Castellano equations and obtain the deformation. For beam structure, the strain energy expressions are integrations m squared over 2EI dx. So again, all you need to do is just take the strain energy expressions and then substitute into the Castellano equations, then you have the deformation. For frame structure, again, they can be considered as a superpositions of truss and beam structures. So they have two terms. One is coming from the thrust or the axial force contribution. The other is coming from beams or the bending moment contributions. And again, quite often that the contributions from the axial force can be ignored. So one single equation, depending on how the strain energies are formulated, it can be used to solve deformations for various structures. So let me show you how you can use these Castellano equations to solve deformations of this cantilever beam. So this beam is undergoing distribute force and concentrate force. And I want to find deformations at the locations where you apply this concentrate force. So first you assume this concentrate force is F and express the internal bending moment as a function of F. Substitute this internal bending moment inside the strain energy expression. And then carry this strain energy into this Castellano equation. Take derivative with respect to F, and then set F equal to 20 kilonewton. Then you will be obtaining the deformation, delta F. You can also use the same equation to obtain deformations at the locations where you don't have any external force, such as you want to find rotation angle at the free end. We call theta A. So what you can do is you can imagine that there's an imaginary bending moment called MA applied at that location. Of course, this is imaginary, it's not the real bending moment, so the magnitude of that should be equal to 0. But you can carry this MA into the internal bending moment. Express the internal bending moment as a function of MA. Carry this bending moment inside the strain energy expressions, and then substitute into the Castellano equation, taking derivative with respect to MA. After you taking partial differentiations with respect to MA, then you substitute MA equal to 0. So after the calculations, that value will be the rotation angle at that particular location.